All right, welcome back. Unit 7 here is we're working with area and volume, and we start off working with the area between two curves. So if we were to graph like two functions g and f, and we want to know what's the area of the section between them from two particular endpoints, well, what we do is we just first we find the area of the top function. So in this case, that would be f. So that's the integral from a to b of f of x. And then we subtract from it the area of the other function. So we would take away this area right here, which is the integral from a to b of the other function. Now, if we're subtracting two integrals with the same bounds, we can put them together in one integral and just say it's the integral of the top function minus the bottom function, which is what we're going to do. All right, so here's an example. Find the area bounded by the graphs of f of x equals 2 minus x squared and g of x equals x. So let's see, I know this is a parabola opening down, and I know this is a line with a slope of 1, but the region bounded by them, I don't really know what that looks like. So what I need to do first is graph both of them and see which one's on top, which one's on bottom, and where they cross. So this one, let's see, 1, 2. It's a parabola opening down, shifted up 2 units. It's going to look like that. And the other one, let me switch colors here, is a line, goes through 0, 0, has a slope of 1, and it looks like that. So it looks like they're both going to cross at 1, because they both definitely have the point 1, 1. And this point back here, if I set them equal to each other, I'm pretty sure we get negative 2. And if you want to set them equal to each other and find out, 2 minus x squared equals x. I'm fairly certain that becomes x squared plus x minus 2, which factors into x plus 2 and x minus 1. So yep, we get 1 and at negative 2. And that point is negative 2, 2. Negative 2, negative 2, sorry. And this was g. All right, and the red one was f. So it looks like if we're trying to find this region, the one on top for the entire region is f. So our integral here to find this would be the integral from negative 2 to 1 of f, which is 2 minus x squared, minus g, which is just x. So if we integrate this, we'll get 2x minus x cubed over 3 minus x squared over 2 from negative 2 to 1. Plug in 1, we get 2 minus a third minus a half. Minus plug in negative 2, we get negative 4 minus negative 8 thirds minus 4 halves. These are going to change to plus. We're going to distribute this negative then, minus plus like that. And let's see, we're going to have a 2 plus 4 plus another 2 is 8. We've got minus a third and minus 8 thirds, so that's minus 9 thirds, and then minus a half. So 8 minus 3 minus a half. So 5 minus a half gives us 4.5, it looks like. All right, hopefully I didn't mess up some numbers somewhere, but that looks like a proper answer. All right, so this area looks like it is 4.5. Next up, the graphs of y equals sine of x and y equals cosine of x cross infinitely many times. Find the area of one region bounded by the curves. Okay, well, let's take a look at those graphs. So sine of x starts at 0, goes up, goes down, goes back up like that. Cosine of x starts high. Oops. It's going to go down. Nuts. There we go. Going to go down again. That's going to be its bottom, and it's going to turn around and come back up, and then it's going to turn back up again. So this is y equals cosine of x, and this is y equals sine of x. This is by no means my best drawing, but it looks like the area is this region right there. And let's see, this is pi over 2, and let's see, this is pi, and then right here would be 3 pi over 2, and this at the end here is naturally 2 pi, and at the start here we had 0. So this where they cross is in the first quadrant. So if we ask where are sine and cosine the same in the first quadrant, well, the two sides have to be the same thing. So that means the hypotenuse would be square root of 2, and this must be pi over 4. The other time it happens is between pi and 3 pi over 2, which is in the third quadrant. And it's going to have to be the same triangle basically, but in the third quadrant. So if I make that triangle in the third quadrant, both of the sides are now negative. This is pi over 4 plus another pi to get there, so that's 5 pi over 4. All right, so that means we're doing just the integral from pi over 4 to 5 pi over 4 of our top one, which in this section was sine, minus cosine, the bottom one, dx. All right, the integral of sine is negative cosine, minus the integral of cosine is sine, and we're going from pi over 4 to 5 pi over 4. All right, now luckily we've already got these two triangles drawn, so we can just read off all the values. So if we start off with 5 pi over 4, where they're both negative 1 over the square root of 2. So we've already got a negative sign from this, and then we get negative 1 over the square root of 2 minus negative 1 over the square root of 2. So that's what we're getting from plugging in the 5 pi over 4. Minus, if we plug in pi over 4, we've got the negative sign here, and we've just got 1 over the square root of 2. And then the negative sign here, and another 1 over the square root of 2. So in the first one, all the negatives cancel. And if we distribute this one, all the negatives cancel. So it looks like we've got 4 of them. We can leave our answer like that if we want, or we can rationalize. And we get 4 root 2 over 2, or 2 square root of 2. It's interesting to me that this section, despite being sines and cosines, does not even involve pi. It's just 2 root 2 is this area between the two curves. All right, let's try the next one here. Find the area of the region bounded by these two graphs. So this guy is cubic, and this guy is quadratic. This one opens down, this one opens up. So my f should probably look something like that. And my g, it's also going to go through 0, 0. It's going to look something like that. And it crosses at 2, and this one I believe also crosses at 2. But it looks like they're going to cross another time back down here somewhere. So if I graph them on my calculator, here's my calculator, there's the graphs. So the red one is the g, the blue one is the f. So I know they cross at 0 and 2. Let's see if we can find that other one. Looks like it's at negative 2, but let's check out for sure. So we're going to go to intersect. All right, we're going to choose, let's see, y1, yep, y2, yep, and take a guess. As long as our guess is close to where they intersect, it's going to find that intersection. So if we take a guess that's close to 0, 0, it's going to come back 0, 0. If we take a guess that's close to this guy, it's going to tell us it's at negative 2, negative 8. So it looks like they cross at negative 2, 0, and 2. So for the first section, from negative 2 to 0, this top graph is f. So we're going to have 3x cubed minus x squared minus 10x on top minus the g, negative x squared plus 2x. Plus, so that's one of the regions, that's this region. Plus, we've got this region. All right, so for this region, g is on top. So we're going from 0 to 2 with this guy on top, the g, negative x squared plus 2x, minus the f, which is all that. 3x cubed minus x squared minus 10x dx. All right, so I could integrate now, or I could simplify first. I'm going to go ahead and simplify first. So from negative 2 to 0, we've got 3x cubed minus x squared minus negative x squared. Those are going to cancel. Negative 10 minus 2x is going to give us a minus 12x. There's our first one. Our second integral from 0 to 2, let's see, we're going to have the negative 3x cubed. The x squareds are going to cancel again. 2x minus negative 10x, so that's plus 10x is going to be plus 12x dx. Notice it's pretty much the same function, just one of them is positive, one of them is negative. All right, so now if we integrate that, that's 3x to the 4th over 4 minus 12x squared over 2, so 6x squared from negative 2 to 0 plus Same thing's going to happen here. Negative 3x to the fourth over 4 plus 6x squared from 0 to 2. And let's see, if we work out all this and we work out all this, I believe they both give us 24. Let me check. 0 is going to give us 0. If we plug in negative 2, we get 16 over 4 is 4 times 3 is 12 minus negative, so plus 6 times 4 is 24. Oh, we are subtracting this guy though. Yeah, so it'll be that. So that'll give us 12. Same thing's going to happen here. If we plug in 2, we're going to get negative 3 times 16 over 4 is 4, plus 6 times 4 is 24. So this also gives us 12. If we add those two up, we do get that 24 is the total area. So each one of them has area 12, and together they give us 24. All right, now we could also go the other direction. So sometimes instead of integrating with respect to x, we can integrate with respect to y, and it's a lot easier. So here, if we integrate with respect to x, we've got to take these functions, and we'd have to solve each one for y. This one is going to have a plus or minus in the answer, so you can have two different answers. One of them will be the positive square root, one of them will be the negative square root, and then you'll be integrating with lots of square roots and pretty nasty stuff happening there. And we'd have at least two separate integrals to do that one. But if we do it with respect to y, it's not so bad. So it looks like they cross at negative 2 on the y-axis and at positive 1 on the y-axis. So the integral would then be from negative 2 to 1 on the y-axis. And it looks like the curve on top is the g, which is the 3 minus y squared. So we do 3 minus y squared minus the line here, which is the other one here, the y plus 1. And we're integrating with our rectangles with a width going up the y-axis, so it's dy. And the height is just the difference between these two curves, which is this inside the integral here. All right, so we can simplify this. That's the integral from negative 2 to 1 of negative y squared minus y plus 2, 3 minus 1, yeah, dy. So we'll get negative y cubed over 3 minus y squared over 2 plus 2y. We're just integrating with respect to a different variable. All right, now if you really didn't like all this y stuff, what you could have done right from the start is you could have said, well, this is going to be the same thing as 3 minus x squared and y equals x plus 1, and then done that problem. And that would get you the same answer. All right, because they're essentially the same curves. It's just switching everything over into the other plane, or the plane the other way around, I guess we should say. All right, plug in 1, we get negative 1/3 minus 1/2 plus 2. Minus plug in negative 2, we're going to get negative, so that's going to be positive 8/3, negative 4/2, and minus 4. Distribute the negative here. All right, so we're going to get, let's say we've got it looks like a 6 here, minus 8/3, plus another 2, so that's going to be 8. Minus 8/3 minus 1/3, so that's minus 9/3, and minus 1/2. So this is 3. 8 minus 3 is 5. 5 minus 1/2 is 4.5 again. Yeah, we got that earlier. So that area is 4.5, and it would be the same thing if we did the area between those two. All right, so that's it for the area between two curves. Next time we'll get a little more complicated with rotating.